as chemists, we'd like to try to understand the physical properties of the world around us from a molecular perspective. And one of the great examples of this is understanding the behavior of gases. There are several physical properties that we can measure for gases in the lab, the pressure and the volume and the temperature. And we'd like to understand how the relationships between those properties are dependent upon the interactions of the molecules. So if we go into the lab, we can do a lot of experiments measuring pressure and volume and temperature and seeing how they're related. And we see there are some very simple mathematical relationships between the properties. And from these we derive the simple gas laws. Boyle's law, Charles' law, Avogadro's law. And we can put those all together into a combined gas law or ideal gas law. But rather than just seeing what the relationships are between the properties, we'd like to understand where they come from. And to do this, we have to develop some kind of physical model. And to get to the ideal gas law, we can come up with a model that says gases are composed of discrete particles which are moving around within the container, and that those particles don't interact with each other at all. And we discover that does a reasonable job of predicting what's going on in the real world, and that's why we assume a lot of gases are ideal and it's a reasonable model. But models are not exact. They don't describe the perfect behavior because they're based on simple assumptions. And so even when they fail, models are useful because they give us insight into the things that we've left out. We start to see the point at which we need to add new things into the model, and we can make it ever more complicated until we have duplicated the exact results in the world.